Okay, so in this lesson, we're returning to exponential functions. Remember, an exponential function's basic formula is y equals a times b to the x, where a is a non-zero constant, and b, which we refer to as the base, has to be a positive number and cannot equal 1. So if you look at some different graphs I've put on here of exponential functions, right here, this particular graph shows why the base cannot equal 1. Because if the base is 1, it never grows or decays, and that is not exponential. It just makes a horizontal line. So that's why the base has to be a positive number, and the base cannot equal 1. Some basic things about any exponential function in this form. A is always the initial value, or the y-intercept. And of course, again, listen to what I'm saying, in this form, if we add or subtract and shift that graph, it will shift the y-intercept. The base is the multiplier, and that's the whole point of exponential functions. They are multiplicative. All right, some characteristics of exponential functions that are really important. The function is continuous. The domain is all real numbers. The range is all positive numbers if a is a positive number, but it's all negative numbers if a is a negative number, because that would make it reflect over the x-axis. The x-axis is the asymptote of the graph. These do plane out. They converge to y equals 0. Again, this is in this form as long as we don't shift it. And so again, like we talked about, the y-intercept is a, and the graphs of y equals a times b to the x and y equals a times 1 over b to the x are reflections over the y-axis. And you can see that if you look at some of these, like for example, y equals 1/2 to the x and y equals 2 to the x, because they are reciprocals of each other. All right, there's two types of exponential functions. When that leading coefficient is positive, there is exponential growth, which is an increasing function. And when we say that, that means it increases for the domain of all real numbers. If I was to ask you, where is that function increasing? You would say from negative infinity to infinity. If I was to ask you where that function is decreasing, you would say never, because it isn't. And then the other situation is exponential decay, and that's when our base is a number between 0 and 1, and it is a decreasing function for the domain of all real numbers. If you were to ask where it's increasing, you would say never, because it does not. What do we do when we have exponential problems that grow or decay by a percent or by a particular rate? Our basic percent growth rate formula is y equals a times 1 plus or minus r to the t. That is the same formula as y equals a times b to the x. The only difference is to get that base, we do 1 plus r if it's growing or 1 minus r if it's growing. You may have learned this formula like this. A equals p, 1 plus or minus r to the t. The next one is our compound percent growth and decay, and that's when it's compounded a certain number of times a year. Again, you also may have learned this formula in the past as A equals p, 1 plus or minus r over n to the nt. And then our last one is our continuous percent growth or decay. So anything that grows or decays continuously in the real world. And that formula you might have learned, I like to call it the PERT formula, as A equals P e to the RT. These formulas are the same. The only difference when you write them with A and P is P is kind of like the principal, especially in money problems. A is your final amount. But the formulas are the same. Okay, so let's do some problems. A lab technician begins with 3 bacteria in a petri dish. Every hour, the number of bacteria doubles. Write a function representing the situation where x is the number of hours and y is the number of bacteria to find out how long it will take the dish to contain more than 100 bacteria. I do this problem with my Math 1 student, so I know y'all can do it. Case, we have our initial value of 3 bacteria. We know that it doubles every hour, so that's our multiplier, so we can use our very basic formula. Put this together, so that would be y is equal to 3 times 2 raised to the x power. If we want to figure out about how long does it take to contain more than 100 bacteria, we can put these in our calculators. In y1, we would put our function 3 times 2 to the x. In y2, we would put in 100, and you would find the intersection. You need to manipulate your window, and at this point, folks, you should be able to do that without my help. And if you find that intersection's at 5.059 So we would say that it takes about 5.059 hours for it to reach more than 100 bacteria. All right, looking at the next problem, a population of a certain animal being researched by environmentalists has been decreasing substantially. Biologists tracking the species have determined the following data set to represent the remaining animals. Okay, so then it goes on to say, assuming the population continues at the same rate, what function would represent the population f of x in year x, assuming x is the number of years after 2010? Okay, so the first thing we want to do in a problem like this is we want to change these years to represent years since 2010. So we're going to let 2010 be 0, 2011 be 1, 2012 be 2, and so on to represent years since 2010. Step 1, we are going to graph this data in our calculator to see what shape it seems to look like. I mean, is it quadratic? Does it look exponential? Does it look logarithmic? Does it look sinusoidal? What's happening here? First thing you want to do is when you go on your calculators, make sure you clear out your y equals, because if not, you might have some graph pop up in there with your scatter plot. And then we're going to go to stat, we're going to go into edit, and we're going to enter this data. Remember, you have to clear out your list. So to do that, highlight L1, press clear, enter. Highlight L2 at the top, press clear, enter. Do not delete those lists. Then in your list 1, put your years since 2010, and list 2, put your population. Sure that you are actually doing this at home and not just watching me do it, because when it comes to a little assessment, I'm not going to help you put stuff in your calculator. So if you don't practice it, you're not going to be able to do it when it matters. The next step is to turn on your stat plot. So to do that, you're going to hit second y equals. You're going to hit enter only first 1 and turn it on. So press enter on. It should already be set up. It's the scatter plot. X list is list 1, Y list is list 2. Go down, pick whatever mark you like. I like the big one because I'm old and it helps me be able to see. And then I'm going to go to zoom, third button at the very top of our calculator, and I'm going to go to number 9, zoom stat. These calculators are really nice because they have a zoom stat that naturally fits your window to the data you have put into your stat. And we can see this has got a curve to it. It may kind of look linear, but if you look at those numbers, they're definitely not linear. And it's got a nice little exponential curve happening. So I think the exponential is going to be better, but what we're going to do is we're going to calculate the ln reg and the x reg, and we're going to write down both, and we're going to compare the r squared values to see which one would be better. So to do that, we're going to hit stat. We're going to go over to calc. We're going to go to number 4, ln reg. We're going to go down to calculate. Press enter, and we're going to write that equation down, and oh my goodness, my r squared's not there because it's not turned on, so we're going to turn that on real quick. So to do that, you're going to press second 0, which is your catalog. You are going to hit alpha D twice so that you don't have to scroll all day long to diagnostic on, and then you are going to go down to diagnostic on. The cool part is once you turn this on, it shouldn't cut off. I'm not sure about the computer one, but in your regular calculators it shouldn't. So we're going to go back to stat, edit, stat calc, and go to number 4, ln reg. We're going to go down to calculate, and bam, there it is. So we're going to write that down. We're going to write down that r squared value. Then we're going to do the same thing for the exponential one. So we're going to hit stat, calc. We're going to go down to, it's option 10, but it says 0, x reg, press enter. Do the same thing again, and we're going to write that down and write down that r squared value. All right, so in comparing those values, what we're looking for is which one is closer to 1. And we can see that the exponential is, so we will go with the exponential function, and that function was f of x is equal to 40,000.158 times 0.75 raised to the x, and that would be the best function to represent this when x represents the number of years since 2010. So number 3, write a function for an account balance with an annual interest rate of 5% and a principal of $30,000. How long will it take to double the investment? Okay, in this case, it doesn't say anything about the money being compounded, so you would just go with your basic percent growth formula, which is y equals a times 1 plus r to the t, and we're going to add the rate because our money's growing. A is our initial amount, which was $30,000, and R is our interest rate, but of course we have to change that to our decimal value. Percent is out of 100, so when you divide 5 by 100, that is 0.05. Okay, so to set up that function, that would give us, and I'm going to call it f of t, equals 30,000 times 1.05 raised to the t. And then we're going to use that to figure out how long would it take that investment to double. So if we start with 30,000, we want to know when it reaches 60,000. So I want y'all to go in your calculators, figure that out, pause the video when you're done, come back, pause now. So if we graph that function in our calculators and we graph y equals 60,000, we will find an intersection around 14.207. The problem is, though, it's an annual interest rate, and it didn't say anything about it being compounded. So therefore, if they only apply the interest once a year, you can't say 14 years because it wouldn't have reached 60,000 yet. You have to round up to 15 years. All right, looking at the next problem, same exact scenario. The only difference is this time it is compounded quarterly. So you're going to work out the same problem, but because it is compounded quarterly, we now have to use our compound formula of 1 plus r over n to the nt. Where, since it's compounded quarterly, n would be 4 because it is compounded 4 times per year, meaning they compounded every 3 months. All right, I want you to pause the video, set this up, get your answer, and then start the video back. Pause now. So in this case, when you find that intersection, it ends up being about 13.949. Now remember, it's compounded quarterly, so that's every 3 months. So we couldn't go with 13 years and 9 months because that would have to be 13.75. So we'd still have to round up. But when we round up to the nearest, 3 months, it would be 14 years. So what we ultimately can see is by this being compounded quarterly versus compounded annually, it took 1 year less for their money to double. Therefore, the more times we compound per year, the more money that they are earning. All right, so then we have our PERT formula. Our PERT formula has that base of E that we learned about in Math 3. E is a very special irrational number that we use for anything that grows or decays continuously. It is that base for anything in the world that's growing and decaying continuously. So let's see an example where we would use this. The population of deer on an island is growing exponentially. The first year the population was 500 deer. 5 years later, there were 552. Write a function that represents the number of deer on the island given the years since the initial population count. So in this case, we are going to use our PERT formula, but I'm going to rewrite it y equals a e to the rt. It's the same thing. What we know is the initial population was 500. And then we know that 5 years later, we end up with 552 deer. So there's 2 ways we can do this. One is we can do it graphically. And what we would do is in y1, we would put 500 e to the 5x, and then in y2 we put the other side of our equation 552. Now remember, in this case, x is representing an extremely small number because it's the rate. Okay, so if we do this algebraically, we would start by dividing each side by 500 to get that base of e by itself. And that would give us 1.104 equals e to the 5r. We would then take the natural log of each side, since this has a base of e in it. And then the natural log of e to the 5r just becomes 5r because the natural log undoes the e. That's the whole property of inverse functions. And we would divide each side by 5, and we would get the same answer as we did when we were graphing. Regardless of how you do it, we put it together. Our function would be p of t equals 500 times e to the 0.0198 t. All right, the next type of problem would be a no calculator type problem. P of t equals 1,440 e to the negative 0.0259 t models the number of mosquitoes in a particular region t days after the beginning of November. Sketch a graph. This would just be a basic sketch. What you should recognize is that the initial value is 1,440 mosquitoes, and that the rate is negative, which means this will be decaying. They are losing the amount of mosquitoes. So all that we would be expected to see on the graph is that you know where it crosses the y-axis, that initial value, and the fact you recognize that this would decay. By what percent is the number of mosquitoes decreasing each day? Again, you should recognize that rate right there. Move that decimal back over. That would be 2.59%. You don't need the negative there because of the fact it says decreasing. How many mosquitoes are in the region in the beginning of November? Again, that's that initial value, so that'd be 1,440 mosquitoes.